Hey guys, welcome back for another SVSU Math and Physics Resource Center tutoring video. My name is Brendon, I'm going to be your math tutor. And for this video, we're going to go over conditional and absolute convergence of series. Alright, hope you guys enjoy it. Alright, let's get into absolute versus conditional convergence. So what we're going to do is we're going to start out with the series as n goes from k to infinity of a of n, just like we do on every other series test. And so what absolute convergence is when we find out using our series test that our series a of n converges and the absolute value of a of n converges, that tells us that it's absolutely convergent. Okay, so now conditionally convergent occurs when our series a of n converges and the absolute value of our series diverges. So that would be conditionally convergent. And so we'll typically see conditional convergence on alternating series that alternate, because the absolute value ends up taking away that alternating term. Okay, and so one thing that, if you remember from the root test and the ratio test, those series when L is less than 1, those series would tell you that it's absolutely convergent already, and that's because the absolute value is built into both of those tests. Okay, so let's kind of see what it looks like for these examples. So first thing I'm going to do for this left example is I'm going to define my a of n. Okay, and so I know that if n is ranging from 1 to infinity, cosine of n, that's always going to be between -1 is less than or equal to cosine of n is less than or equal to 1. Okay, so cosine is always going to range between -1 and +1, right? So if I let b of n equal 1 over n squared, we know that this series converges from the p-test. P is equal to 2, which is greater than 1, which tells us that it converges. Okay, so if I'm letting b of n be 1 over the square root of n, and I know cosine is always less than or equal to 1, then that tells me that our series, our a of n, is always going to be less than or equal to b of n. So by direct comparison, that tells us that a of n converges. Let me rewrite that. A of n. Okay, so that tells us that a of n converges, right? So now let's go ahead and take the absolute value of a of n. So this is going to be the series as n equals 1 to infinity of the absolute value of cosine of n divided by n squared. Okay, so now if we're taking the cosine, right, of our n squared was always positive terms, right? So the only thing that's going to change is our numerator, right? So instead of ranging from -1 to 1, our cosine is now ranging from 0 is less than or equal to cosine of n is less than or equal to 1. Okay, so that's what the absolute value does to our series. Okay, so again, we're going to let b of n equal to 1 over the square root, 1 over n squared, which is still a converging p series, right? And so if our cosine is still less than or equal to 1, that tells us that a of n is still less than or equal to b of n. So then that tells us by direct comparison that a of n converges. Okay, so when we went through and we found that our series a of n converges, and then we also found that our absolute series of absolute value of a of n converges, that tells us that this is, or converges absolutely. Okay, all right, so now let's go over to this problem. All right, so first thing we're going to do is we're going to specify our a of n term. Okay, and so what we want to do is we want to do it looks like this is an alternating series, so let's go ahead and do the alternating series test. Okay, so our alternating series test, we need to show that our A of n, well actually let me rename this because the alternating series test we need to specify our B of n. So, well actually this is going to be A of n and our B of n is going to be equal to, without the alternating term, so 1 over n. Okay, so for the alternating series test to show convergence, we need to show that B of n is decreasing, right? So if our n is going from 1 to infinity, our denominator is just going to be getting bigger and bigger and bigger. So that tells us that our expression gets smaller and smaller and smaller. So we're decreasing there. So let me put a decreasing. Check. Okay, so now we need to take the limit as n approaches infinity of B of n, and we want that to be equal to 0. Okay, so this is going to be the limit as n approaches infinity of 1 over n. And so that's going to be equal to 0 because infinity, our denominator, is going to get really, really big. So our expression is going to go to 0. So that, I'll put a check over here by this one. Check. Okay, so then that tells us through the alternating series tests that the series as n is equal to 1 to infinity of negative 1 to the n plus 1 over n converges. Okay, and so now what we're going to do is we're going to take the absolute value of that. So this is going to be the series as n is equal to 1 over infinity of the absolute value of negative 1 to the n plus 1 over n. Okay, so this is actually just equal to the series as n is equal to 1 to infinity of 1 over n. And so if we have the series of 1 over n, this is just our harmonic series, right? And we know that our harmonic series diverges. So then that tells us we know that our series of a of n converges and our series absolute value of a of n diverges. So then that tells us that this series n is equal to 1 to infinity of negative 1 to the n plus 1 divided by n converges conditionally. Okay, so these are two examples, one that converges absolutely, one that converges conditionally. And so then you might be wondering, well, what about divergent? Is there such a thing as conditional divergence? And there isn't. So if your series diverges, it's going to always diverge. Okay, hope you guys enjoyed the video. Thanks for watching.